Welcome to my virtual talk. I'm Greg Botham from the Department of Physics at the University of Oregon. I'll mostly be off camera. I'll be on camera now. I'm one of the organizers of this conference, but we didn't have enough oral time slots for me to deliver this orally, and that's unfortunate because some of this presentation involves images and data that's actually moving. It's hard to capture in poster form. But I'd like to present something briefly on a relatively new way to analyze noisy climate data through waveforms. People are familiar with this in terms of visualizations, but it's also quite a handy analysis tool. So for the purposes of this talk, I'm focusing exclusively on wintertime climate precipitation waveforms, where wintertime is defined as November through February, that 4-month period. Now, this technique has been applied before, mostly by people that are outside the climate community, but power spectrum and wavelength transformation analysis has been done in papers starting in the late 90s. That one's from 1999. You see the word wavelength transformation. And here we have more power laws and wavelength transformations. So this is not a new technique. We apply it in a slightly more simplified and intuitive manner, I think. So, oops, probably shouldn't have drawn on that, but not going to erase it for now. Still read it. In general, regional climate data represents random noise on top of multi-decadal fluctuations. Might even be better over here. This is a bunch of randomly simulated data. Each color represents a random simulation. It's completely dominated by noise, but you can see sort of in this purple one, there's a vastly fluctuating baseline throughout. That's obviously extreme. But that's the nature of the data that we have to deal with in terms of fluctuations, large random variations on a fluctuating baseline. And when you use wavelets or Fourier transforms or anything like that, your results are really pretty much noise dominated. Get rid of these things. And so you can really have limited information on various large spatial and temporal scales. And we would like to avoid that limitation. And so what we've done is use the following simplified approach. We form a z-score, number of standard deviations above or below the mean a particular site has relative to a baseline of 100 years. We employ adaptive kernel smoothing. This is significantly better than standard moving average or boxcar smoothing. It weights the most proximate years. We use a Gaussian filter for our kernel with a width of 7 years. We have good data for 29 inland sites in western Washington and Oregon, and we weight the data somewhat by the reliability. So each site has a monthly z-score generated compared to a 100-year baseline. And then the combined weighted 4 months of all sites produces that year's z-score index. So it's probably best at this point to shift to a graphical representation of this, to show you one of our principal results, which is for spring time, just to show that we can produce a result. And so there you see some data for the springtime z-score. And here's actually a well-known drought that occurred in the late 20s. Zeros right there running across. And then we can see sort of normal fluctuations in this, and here we go until very recently. Should have paused it, but I didn't. Very recently, as anybody that's paying attention to the weather, in the last 4 springs, from 2008 to 2012, I guess that's 5 springs, noticed that they were very cool and wet. In fact, the 2010 Pacific Northwest Climate Conference held in Portland on June 15th, it was 50 degrees and raining at noon on that day. Perhaps some of you remember that. But this is a very, very strong signal. It's unmistakable. It's an example of a signal that can be generated by our technique. So we can apply that now to the winter time. signal, and let me just show you that here. So we start off, and again, zero's right there, so try to follow the zero line with your eye. We start, in 1900. All this data starts in 1900. And so we see there two pronounced wintertime well-known droughts. The one that occurred in the late 20s and the one that occurred during World War II. Notice that these are relatively sharp features. Since we are weighting our kernel width is 7 years, that means that these features are usually dominated by 1 or 2 excessively dry years. And as we'll see when we get to the early 90s, it's excessively wet years. So we'll keep this going. And not much is happening in here. No droughts, no pineapple expresses. And then there's another big feature that appears here in the late 70s. It's big, relevant to that peak in the early 70s. So in the early 70s, we were excessively wet. Paradise Ranger Station set the world record snowfall in 1972. That was broken a few years ago at Mount Baker. But that's a really big volatility signal there. And so the late 70s, we enter a bit of a dry period, but then we rebound from that. And now we're almost to the time scale of interest. And there you see the big Pineapple Express peak of 1996 that caused the floods, and was also wet in 1995 and the like. But since 2000, we've had this dramatic drop. 2000 is the first point that's right here, and it's below zero. And this is the feature that I want to talk about. So let me play this again. And you can see lots and lots of fluctuations. And then this feature, all below zero with low volatility. And that will form our principal waveform result. So that's it for moving data. And now back to the PowerPoint. Just a second here. Okay. So this is our example signal that you saw before from spring, where you can see that where the mouse pointer is now, a tremendous rise in wet springs, which was broken this year in 2013. Broken dramatically. It's quite dry. Now this is another project, but I just want to show an example of another signal. In this case, the signal is to the right with that strongly rising feature, which it represents the American Northeast, this feature here that we're talking about. And it's moving in the sense that summers in the American Northeast, combined of 9 states in our analysis, are becoming significantly wetter and more humid. You can see that in airport delay statistics for the last 5 years due to thunderstorms and the like. So this is an extremely significant signal. It's the strongest signal that we have in any of our analysis in any region in the United States. Excuse me. And this is about to be submitted for publication. But these are the kinds of things that can be generated. There's something odd in the data, numerically, is that each one of these red dots, which represents the maximum or minimum amplitude of one of these features, is separated by about 40 years. I have no idea what that means. Now here's the result that you saw before, the wintertime waveforms that we get. The feature we're focusing on is this flat feature. That's the total Washington plus Oregon, and then the individual Washington and Oregon data sets are shown. Overall, Washington exhibits slightly more volatility than Oregon. I think inland western Oregon is a little bit more of a homogeneous terrain than inland western Washington. There is a significant difference between Washington and Oregon right here. And that feature doesn't appear at all. In fact, it appears in inverse in Oregon. It's like that period, the two climate systems are slightly anti-correlated. But overall, the waveforms show the general large-scale feature. This is what I mean by increasing volatility in Washington. You see none of this down here. Here it's relatively flat. But in recent years, you see that matching up to that, and you see the big Pineapple Express peak matching there. But more importantly, both things, both states, not things, show evidence for this below normal sustained wintertime precipitation with relatively low volatility around that. Again, that's our principal result at the moment. And there it's highlighted. There's a feature of interest. And now you can do some things statistically with this. You can simply integrate on the area under this curve to 0 to count the total number of negative pixel area in here, and then slide that box down and see if is there any other 13-year period which has the same amount of total negative pixel area. And the answer is no. The total negative pixels here are significantly larger than there and there because these are relatively short timescale features, especially that one. And so this is a unique feature in the data. You don't see any part of the data here showing this kind of thing. Only in this period right here do you see a period of low volatility, but its average is pretty much around 0. You don't see anything with below 0, and again, these are index scores, standard deviation scores on the y-axis, smooth with a Gaussian of 7 years. And here's the actual individual data in the background you can see. The average of the individual data standard deviation is 0.3 in units of z-scores. That number will come back later when we do a quick random test. So this is the claim that we're making. I don't really expect anybody to believe it. More on that later. But this is the feature that manifests itself in a statistically significant way in just counting statistics that appears when you produce this weighted waveform smooth over 7 years. So that is the climate change box. That's what it looks like in the winter season indexed this way. Now, most of you are sitting and saying, well, hell, this is just all noise. I don't believe a word of this. And it's hard to believe any of this unless you've actually spent a long time doing this kind of analysis. My background is astrophysics, and I do this kind of analysis all the time, but hell, in astrophysics, we only care about order of magnitude. But here is just an example of two hypotheses, one in which there's been no change over 100 years, and all the features that you saw in the waveforms are random fluctuations at either a level of 0.3 or 0.5 standard deviations, and it doesn't even come close to matching the data. This scale only goes from minus 0.2 to plus 0.2, whereas the scale of the fluctuations in the actual smooth waveforms are an order of 2.5 times larger, from minus 0.5 to 0.5. So in no way can you produce the kinds of large-scale fluctuations, minus 0.5 to 0.5, that are seen in the actual data. This just doesn't suffice. And I remind you that the actual measured standard deviation in actual data is 0.3. So this top box with the 0.3 random noise added is more appropriate to the data. We just decided what happens if you try and add even more noise. You still don't get the same amplitude. In the temporal domain, you can get these multi-decadal features, which are just noise, but their amplitude is much, much lower than the real data. Now, we have taken a look at wintertime snowfall. Come on camera again just to remind you what's happening here. And this merely confirms what everybody else has known, is that wintertime snowpack is gradually reduced. And this is the late 70s right in here. And you can see that since this time, and there's about 11 sites in western Washington that define this particular waveform, going back to 1935 or so, because finding reliable snowballs prior to that time is pretty hard. So some of this large-scale noise and fluctuations may be data reliability problems. We're still in the process of determining that. But nonetheless, you can see that the total amplitude in here is much, much less than the amplitude in here, and the mean value is significantly lower than it is there. This most recent little tiny rise here is dominated entirely by the La Nina 2006-2007 event, which did produce a lot of wintertime snowfall in the Cascades, especially in April of 2007. There was a slightly minor event that's kind of escaped people's notice that happened in 2009. But you can see here it's 2008, way down among the among the lowest in the entire data set. And so this small rise is really a consequence of, again, being dominated by a couple of years within a 7-year smoothing window, and it's a relatively small rise. So this is just a confirmation of what we already know in terms of reduced snowpack. So let me finish here. I think I'm well under 20 minutes. So what is presented here, we have a very large subset of data broken out by season, min temperature, max temperature, soil temperature, whatever. It's all the same analysis. It's all the same machine. So we just feed data to the same machine and turn the crank. And we have lots and lots of seasonal waveforms and lots of results from that. Community unfamiliarity with this kind of analysis is actually a problem. It limits the effectiveness of the approach, and it limits understanding the power of waveforms to be used as a statistical tool. In other disciplines, the limitation is not really there. This is sort of a common thing to do with noisy time series data. But this hasn't been applied very much in the climate community. But the bottom line is we make this argument. Now, I'm tired of being on camera. So, this wavelength feature, 13 years long, to us represents the new waveform of wintertime precipitation that Western Oregon and Western Washington is now going to experience now and forever. This is characterized by two features: significant deficits compared to long-term averages, and I think anecdotally and even other ways of analysis is consistent with that. But more importantly, and this is what the waveform analysis really shows you, much significantly less volatility. Winters are not bouncing back and forth between very wet and very dry, or having periods of very wet followed by periods of very dry. The volatility has been greatly reduced. So based on all of this, quantitatively, which is another talk, we predict that in the near future, or maybe long-term future, total seasonal precipitation values in the 4 winter months of November, December, January, and February are going to be 30 to 60% below the traditional late 20th century values, what you grew up with between 1950 and 2000. We're going to be 30 to 60% low across inland Washington and inland Oregon. A point I should have made earlier is we're not including coastal communities like Astoria or Seaside or Long Beach. We're just talking about inland Oregon and inland Washington, to the extent that inland Oregon and inland Washington merge with the Western Cascades. That's the region. So that's my talk that I didn't give at this conference. The poster will be there. I may or may not be near my poster to answer questions. There will be a QR code on my poster that you can simply scan with your mobile device that will launch this talk, which is now on YouTube. So thanks for your time, thanks for your attention, and seriously, be somewhat tolerant of this waveform approach to analyzing noisy data, because it's powerful and it can work. Thank you.